Conceptual understanding of independence. Welcome, everyone. Today, we are going to dive into a very important concept in probability known as conceptual understanding of independence. Now, as you progress in your study of probability, you'll notice that we rarely look at just a single, isolated event. Instead, we often encounter much more complex situations where two or more events occur, sometimes simultaneously or in sequence. As we analyze these multiple events, a fundamental question arises that we must learn to answer. Does the occurrence of one event provide us with any useful information about the likelihood of another event occurring? In other words, does knowing the outcome of the first event change our prediction for the second? This very question, the search for whether one event carries information about another, is what leads us directly to the core concept of our lesson today: independence. Intuitive definition of independence. At its simplest level, we say two events are independent if the occurrence of one event has absolutely no effect on the probability of the other event occurring. To put this another way, imagine we have two events. Let's call them event E and event F. If these two events are independent, then even if I tell you that event E has already happened, that piece of information doesn't change your estimate of the probability that event F will happen. Your prediction for event F remains exactly as it was before. Essentially, what we are saying here is that the influence, or the impact of one event on the other is zero. Now that we've introduced the idea that we are looking for connections between events, let's dive into the intuitive definition of independence. In the next few slides, we are going to use a deck of cards to see exactly how this looks in a practical calculation. Detailed example, drawing a card. Now that we have established the intuitive definition of independence, that one event having no impact on the other, let's move from theory to a concrete example to see this in action. To understand this concept more clearly, let us consider a standard deck of 52 playing cards. In our scenario, we are going to draw just one card at random from this deck. To analyze whether these events are independent, we first need to be very precise about what we are looking for. So, in step 1, we will define our two specific events. Let event E be the event that the card drawn is a spade, and let event F be the event that the card drawn is an ace. Keep these two definitions in mind, because in the next slide, we are going to calculate the probabilities for each and see if knowing one actually changes the likelihood of the other. Probability calculations for drawing a card. First, let's look at step 2, where we calculate the initial probability of event E, which is drawing a spade. As we know from our standard deck, there are 13 spades out of 52 total cards. So, the probability of E, written as P of E, is 13 over 52, which simplifies to 1 over 4. Next, let's move to step 3, where we analyze what happens to that probability if we are given extra information, specifically, if we know that event F, drawing an ace, has already occurred. Imagine you are holding the card and I tell you, I can confirm this card is definitely an ace. Now, ask yourself, does this new information change the likelihood that the card is a spade? To find out, let's look only at our new sample space. We are now only concerned with the 4 aces in the deck. Out of those 4 aces, how many are spades? Only one, the ace of spades. Therefore, the probability of E given F, which we write as P of E given F, is 1 over 4. Now that we have defined our two events, the spade and the ace, let's move into the actual calculations to see if they are truly independent. Notice that this value is exactly the same as our original probability. Keep this result in mind, because in the next slide, we will compare these two values to reach our final conclusion. Comparing probabilities for independence. Now, let's move on to step 4, where we compare our results to reach a final conclusion. If you look at the calculations we just performed on the previous slide, you'll notice something very important. The probability of event E, which is the probability of drawing a spade, is 1/4, and the conditional probability of E given F, meaning the probability of drawing a spade, given that we already know the card is an ace, is also exactly 1/4. Because these two values are identical, it shows us that the probability of event E remains completely unchanged, regardless of whether event F has occurred or not. Therefore, based on this mathematical evidence, we can formally conclude that the events drawing a spade and drawing an ace are independent. In the next slide, I'll show you another example involving a coin and a die to reinforce this idea of separate, unrelated processes. Real-world example, separate experiments. Now that we have seen how independence works within a single deck of cards, let's shift our focus to a slightly different perspective. Independence is often most easily observed when we look at two events that come from entirely different physical processes, meaning they aren't even part of the same experiment. To illustrate this, let's consider a new scenario. Imagine you are tossing a fair coin and rolling a fair, six-sided die at the exact same time. To analyze this mathematically, our first step is to clearly define our events. Let's call event A the event where the coin lands on heads, and let's call event B the event where the die lands on a six. Evaluating influence in separate experiments. Now that we have defined our two separate events, the coin toss and the die roll, let's move on to step 2, where we evaluate the influence of one on the other by looking at their individual probabilities. First, let's look at the coin. Since we are using a fair coin, the probability of event A, which is the coin landing on heads, is 1/2. Next, let's look at the die. For a standard six-sided die, the probability of event B, which is rolling a 6, is 1/6. At this stage, we are simply establishing the baseline probabilities for each event before we compare them to see if they truly are independent. Logical conclusion for separate experiments. Now that we have calculated the individual probabilities for our coin and our die in the previous slide, let's move on to step 3, where we reach our logical conclusion. Ask yourself this: does the result of the coin toss actually change the physics of the die roll? Of course not. The coin and the die are two separate physical processes. Whether the coin shows heads or tails, the probability of rolling a 6 remains exactly 1/6. Because the outcome of the first experiment, the coin toss, has absolutely no effect on the outcome of the second experiment, the die roll, we can confidently state that events A and B are independent. This brings us to our next slide, where we will summarize the key takeaways of this entire concept. Key takeaways on independence. First, if you remember nothing else, just remember that independence simply means no influence. It is the absence of any connection between the likelihood of two events. As we saw in our previous examples, we say two events are independent if the knowledge of one event occurring does not alter the probability of the other event occurring. In other words, getting extra information about one event doesn't change your original estimate for the other. To put this into a formal mathematical language that you can use in your calculations, if P of E represents the probability of event E, and P of E given F represents the probability of event E occurring, given that event F has already happened, then for independent events, P of E given F equals P of E. This formula is the mathematical way of saying that the given part, the occurrence of F, has had no impact on the probability of E. Now that we have looked at the card example and the coin and die experiment, let's bring everything together with some key takeaways. Now, before we move on, I want to warn you about a very common pitfall that many students encounter, so please pay close attention to the next slide. Common mistakes to avoid. First, please be very careful not to confuse the concept of independent with mutually exclusive. This is, hands down, the most common error for beginners in probability. It might sound like they mean the same thing, but they are actually very different. Remember what we discussed in our earlier examples. Independent events can, and often do, happen at the same time. The only thing is that the occurrence of one simply doesn't change the likelihood of the other. However, mutually exclusive events are a different story entirely. These are events that absolutely cannot happen at the same time. In fact, if one event occurs, it completely prevents the other from happening. This means that mutually exclusive events actually have a very strong influence on each other. If I tell you one has happened, you know for a fact the other hasn't, which is the opposite of the no influence rule we learned for independence. Second, a word of caution. Avoid the temptation of assuming independence without proper verification. In everyday conversation, we might say two things are independent just because they seem unrelated, but in mathematics, we cannot rely on intuition alone. You must always verify independence using the formal probability rules, such as checking if the probability of E given F is equal to the probability of E. We will be covering those specific mathematical proofs and rules in the subsequent sections of this chapter, so make sure you follow along closely when we get there. Now, before we move on to our next lesson, I want to pause here on this final slide to address two critical pitfalls that even advanced students often fall into. That concludes our conceptual introduction. Great job today!